Hello everyone. Today we will be talking about solving linear systems, which will involve how to do it for simple situations, and then we'll also be talking about a couple of matrix decompositions that are helpful for solving linear systems. So let's zoom in here. So here's the problem. We have an n by n matrix A and an n by 1 vector B. Both A and B are given to us. And we would like to compute A inverse times B, which will give us in our notation x. So here the A and the B are given and known, and we want to get x. Now, of course, this assumes that A inverse exists. It doesn't always exist for any n by n matrix, but for the purpose of this material, we will be assuming that the inverse does exist. So it's a non-singular matrix. So just to see an example of where this is a really important problem for statistics, on the right here I have the expression for the generalized least squares estimate for design matrix X. So X is going to have n rows and p plus 1 columns, and covariance matrix sigma. So sigma is the assumed covariance matrix for the observations, and that's an n by n matrix. And then of course we have the data vector y, which is an n by 1 vector. So you can see that there's, if you stare at this expression, there's three inverses that occur. Reading right to left, we have to do sigma inverse y. So this is exactly what our problem looks like here. We also have to do a sigma inverse x. So since x is a matrix, n rows and p columns, this means you have to do, or p plus 1, however you want to define it. This means that you have to do p plus 1 solves, or matrix inverse times a vector. And then we have another one here. We have the inverse of this entire expression multiplied by x transpose sigma inverse y. All right, so the way this usually works is that we recast the problem in the following way. So this is the expression that we're trying to evaluate up here. If we just multiply on the left by a, we get ax equals a inverse b, which equals b. So the problem becomes find x such that a times x equals b. So why is this allowed to multiply on the left by a without changing the problem? So this generally is not allowed unless a is a squared non-singular matrix. So because of that, we haven't changed the problem at all by rewriting it as a times x equals b. Now, if you remember from your linear algebra course or matrix algebra course, this corresponds to a set of linear equations, ax equals b, with known b, known a are the coefficients, and unknown x vector. Here x, of course, is an n by 1 vector. So just giving you a little bit of notation here, if we write out the vector x in the following way, so here I'm just using a lowercase letter without subscripts to be the entire vector, and then we subset it with subscripts. Same thing for b, and then I'm going to use the lowercase of a with subscripts to denote the entries of the matrix A. So if we take this expression, this matrix expression, ax equals b, and then write out the expression in terms of the coefficients in these various objects, we get this here. So these are the system, this is the system of the linear equations that we would like to solve. So the idea here is we know the b's, we know the coefficients a, I, j, and we need to recover the x's such that these equalities are true. Okay, so how the heck do I solve this? In general, it's kind of hopeless. You can't just figure it out by looking at it. But there are some situations where you can, where figuring it out is actually kind of easy. And we're going to look at 3 or 4 different situations. The first 2 are kind of similar, so let's go through those. If the coefficient matrix A is the identity matrix, this is like the easiest possible situation, then this system of equations AX equals B corresponds to IX equals B, and therefore X equals B. Okay, so this is kind of like a non-example, that if you multiply by the identity matrix, you just get the vector back. So this is a really easy one. If A is the identity matrix, X is just B. Now let's go to a slightly more complicated one. If A is a diagonal matrix, but not the identity, we write it like this: A equals diag A11 up to ANN. So what this means is you have a n by n matrix, and all of the entries of the matrix are 0 except for the diagonal entries A11, A22, A33 up through ANN. If A is diagonal, then you can write down the system of linear equations. So if we stare at this, if all the off-diagonal ones are 0, then things like A12 are 0. This will go away. A13, A1n, those are all 0. So you get A11, X1 equals B1. Here for the second one, this will be 0. Then you get A22, X2 equals B2. And down here, you just get ANN, XN equals BN. So that's exactly what we have written here. And now, this is a simple enough situation that you can just solve it. So here, X1 is equal to B1 over A11. That's what we get here. And this is true for all of them. So Xi is just going to be Bi over Aii. So Xn is Bn over Ann. Now, this solution only works if all of the AIIs, all of these diagonal entries, are non-zero. So if one of these, if A11 were 0, you wouldn't be able to do B1 divided by A11 because you can't divide by 0. But that would violate our assumption here that the inverse exists. So if you have a diagonal matrix with one of the entries being 0, then the matrix is singular and it doesn't have an inverse. So by assumption, all of these are non-zero. Okay, so let's go to a little bit more complicated one. If the matrix A is orthonormal or orthogonal, what that means, so orthonormal, what that means is if you do A transpose times A, you get the identity matrix back. And what this means is that, well, if you take any matrix and multiply it by the input matrix A, and you get the identity matrix, then this matrix that you multiplied it by must be the inverse. So orthonormal matrices have the property that their inverse is equal to their transpose. And this happens when each column of A is orthogonal to every other column. And the difference between, well, let me come back to that in just a second. So just to give you some notation for what that means, if I write out the matrix A in the following form, A1, A2 up to AN, you notice I just have one subscript here. What I mean by that is A1 is the first column of A. So A1 is an n by 1 vector, so you can imagine extending this down. A2 is also an n by 1 vector, and A1 is an n by 1 vector. So A1, A2, AN are all n by 1 vectors, and they define the columns of A. And if we were to take the inner product AI times AJ, in an orthonormal matrix, the inner product is 1 if I equals j, and it's 0 if I is not equal to j. So the zeros are where the orthogonal part comes from, and the 1 is where the normal part of orthonormal comes, meaning the vectors have length 1. Okay, so that's just the definition of orthonormal. By the way, orthogonal generally means that you get zeros if you do I not equal to j, and you're allowed to have something not equal to 1 if you do AI transpose times aj. So the normal gives you the 1s. Okay, and we'll see an example of that in just a second. So if we want to solve ax equals b, this is really simple. We just do A transpose, multiply both sides on the left by A transpose. So you get A transpose AX equals A transpose B. And by the orthonormal property, A transpose A is the identity, so this part goes away, and you just get X equals A transpose B. All right, so that situation is really simple when you have a pretty special matrix A, which is orthonormal. Up next, we're going to look at a numerical example that combines situations 2 and 3. Okay, so here's our orthogonal diagonal example. So here's the matrix A. It's a 3 by 3 matrix. The first column is 1, 2, 1. The second column is 1, 0, minus 1. And the third column is minus 1, 1, minus 1. Now, if we take the inner product between any two columns, we get 0 every time. So let's just do this for fun. A1 transpose A2 is the inner product between the first two columns. So it's going to be 1 times 1, which is 1, plus 2 times 0, which is 0, plus 1 times minus 1, which is minus 1. So 1 plus 0 minus 1 equals 0. A1 and A3, you'll get 1 times minus 1 is minus 1, 2 times 1 is 2, and 1 times minus 1 is minus 1. Add those up, you get 0. A2 transpose A3, 1 times minus 1 is minus 1, 0, 1 gives you 0. So this is a matrix that has orthogonal columns. However, the columns are not normal because their lengths are different from 1. So for example, just look at the first column. If you take the dot product of it with itself, you're going to get 1 plus 4 plus 1, which is 6. Second one gives you 2. Third one gives you 3. So if I do A transpose A, I don't get the identity matrix. I get a diagonal matrix. 6, 2, 3 on the diagonal. So let's call that matrix D. So very clearly we see that this actually doesn't fall neatly into one of these two categories. It has sort of aspects of both of them. So to solve the system, we're going to end up using both of those aspects. So A transpose A is a diagonal matrix. And our right-hand side vector B, I'm just going to make 1, 4, 3 for the purpose of this example. And let's just start doing some math. So this will probably get simplified if we multiply left-hand side by A transpose. So A transpose AX, A transpose B. We define A transpose A to be this diagonal matrix. So we get dx equals A transpose B. And if we write everything out, so what does dx look like? Dx looks like d times x. So it's just going to be 6 times x1, 2 times x2, 3 times x3. So this becomes our new left-hand side. And if we do A transpose B, these are all just, there's no variables here. If we do the matrix multiplication, we get, let's see, 1 plus 4 times 2 is 8, plus 1 times 3 is 3, you get 12. 1 times 1 plus 0 minus 3 is minus 2. Minus 1 times 1 plus 4 minus 3 is 0. So A transpose B, which is on the right-hand side here, is 12 minus 2, 0. And then if we just take, this solution, this is dx, and this thing here, this is A transpose B, which is this, and write out the equations, we get 6x1 equals 12. That's from here. 6x1 equals 12. 2x2 equals minus 2. 2x2 equals minus 2. And 3x3 equals 0. Now this is something we know how to solve. And so we just divide by these coefficients. So we get x1 equals 12 over 6, which is 2. x2 is minus 2 divided by 2, which is minus 1. And x3 has to be 0. 3 times 0 is 0. So our solution is 2 minus 1, 0. And whenever you get a solution, it's probably a good idea, especially if you do it by hand, to check it. So I'm just setting up the original problem here, a times solution x, and doing the matrix multiplication. I'll save you the details, but here are the details. And you get 1, 4, 3. And let's double check. What was our original b? Yep, it's 1, 4, 3. So we get a green check mark here. So what we just checked is we found the vector x, 2 minus 1, 0, such that a times x equals b. And how did we do it in this example? We used the property that a is orthogonal but not orthonormal to transform the problem to dx equals a transpose b. So this is kind of interesting because now we have a new right-hand side that is known. So this is like our new b, a transpose b, which is this vector here. And our left-hand side falls into the diagonal category. So this matrix D times X, D is diagonal. Now it's like we've recast a new problem into diagonal form. Dx equals new vector over here. And this we know how to solve. We just use the diagonal solving algorithm, which is very simple. Okay, so that's an example where it doesn't fall neatly into one of the previous categories, but we can use properties of both of those categories, diagonal and orthogonal, to solve the system. Okay, the last category of matrices we're going to look at are called triangular matrices. So there's lower triangle and there's upper triangle. I'm going to show you the examples with lower triangle, but the upper is very similar. So what lower triangle means is that all of the entries of A are 0 if you're in what's called the upper triangle of the matrix. So the lower triangle is down here. The upper triangle is up here. So lower triangle really means lower left triangle. And upper triangle really means upper right triangle. So this is lower triangle. Now if you're working with a lower triangular matrix, the entries of the diagonal are allowed to be non-zero, and we'll see they actually have to be non-zero in order for this matrix to be non-singular. If we were working with an upper triangle, again the diagonals would be non-zero, but these would be also non-zero, but these ones would be 0. Okay, now in kind of mathematical notation, what lower triangular means is that coefficient aij equals 0 if j is greater than I. So let's just look at an example. So if we're looking at A13, that is this entry here, 3 is bigger than 1, so therefore this has to be 0 in a lower triangular matrix. All right, so that's just what it means in picture and in sort of mathematical notation form here. Oh, by the way, the determinant of a lower triangular, or determinant of any triangular matrix, lower or upper, is equal to the product of these diagonal entries. So that's why in order for a lower triangular matrix to be non-singular, all of the diagonal entries have to be non-zero, because if you get 1, 0 along the diagonal and you're taking the product, then the whole thing has to be 0. You know, that reminds me of a math trick my dad told me when I was a kid. He said, what is the product of the number of hairs on all people's heads in the whole world. And as a kid, that's kind of like, oh, that must be a huge number. But once you realize that there's at least one person with 0 hairs on their head, then the product has to be 0. Okay, so same works for determinants of triangular matrices. So let's take this lower triangular form. I'm going to put the whole thing on the same page. And we're going to write out the linear system of equations, ax equals b. And I'm going to do it a little bit different. I'm going to put b on the left-hand side and ax on the right, just because it looks nicer when you line them up that way. So if we look at this first row, we're going to get a11 times b1 plus a bunch of zeros. So that becomes, a11 times x1 plus a bunch of zeros equals b1. So the first equation is b1 equals a11 x1. The second one, we're going to do a21 times x1 plus a22 times x2 plus a bunch of zeros equals b2. So that's here. b2 equals a21 x1 plus a22 x2. And you can see what happens as you move down each equation. You're going to get one additional term. And the one additional term is going to involve a new x. And it's going to be multiplied the diagonal times the new x. So let's just do b3. You'll get a31 x1 plus a32 x2 plus the new x is a33 x3. And that's equal to b3. So that's here. And the very last one, you get all of the x's multiplied by an a. So this may look a little bit daunting, but the strategy here is to just go ahead, start at the top, and try solving it. So the first one's easy. This looks just like the diagonal case. So we're going to have x1 equals b1 divided by a11. So that's here. Now let's look at the second one. Well, if we just rearrange things in terms of x2, we get this. b2 minus a21 x1, the whole thing divided by a22. So I'm just doing the algebra to rewrite this. So this is interesting. However, generally you're not allowed to write the solution of one of them in terms of the other unless you've already figured out what the other one is. And in this case, we have. We've already figured out what x1 is from the first one. So this is okay. So I'm thinking if I have these two numbers, I now have x1 as a number. And then everything on the right-hand side here, b2 is a number I have. a21 is the entry of the matrix A. It's a number that I have. It's given to me. x1 wasn't originally given to me, but now I have it here. And a22 is given to me. So I can get x2 here, no problem. If I look at x3, I rearrange this. I get b3 minus a31 x1 minus a32 x2, whole thing divided by a33. And you can see that conveniently now I know b3, a31, a32, and a33. Those were all given to me. I already know x1 from the first equation, and I already know x2 from the second equation, which required me to know x1. So you can see that these will build upon each other. And it's because of this property that each successive equation only adds one additional x. And so if I've figured out what these previous x's are, then I can rewrite things to have an expression for the new x. So that's exactly how this works, all the way down to xn. So this algorithm, I guess you can call it an algorithm, is called forward substitution. All that means is we start at the top, we start at the first one, we move forward, x1, then x2, x3. Each time we're substituting in the known value of the previous x's. Now, for upper triangular systems, you can kind of guess what would happen is that one of the last equation would be like ANN times XN equals BN. So the last equation, you can figure out what XN is, and then you could start working backwards. So as an exercise, go ahead and write out an expression for an upper triangular matrix. I think I have later in the notes. Let me just remind you what that looks like. We're skipping ahead, but I just want to show you. So this is an upper triangular matrix. So imagine multiplying this by a vector x, setting it equal to another vector b. You're going to get UNN times XN equals BN. And therefore, you can rearrange and figure out what XN is. And then the next to last one is going to be like UN minus 1, N minus 1 times XN minus 1 plus UN minus 1, N times XN equals BN. And you can just substitute in and go backwards. So that's why it's called, for upper triangular systems, it's called backward substitution. Now let's make this a bit more concrete by looking at an example with numbers. So here's our example. We have the matrix A, which is lower triangular and non-singular because there's non-zeros on the diagonal, 2, 4, 6. It's lower triangular because everything to the top right of the diagonal is 0, these 3 entries. So A is a nice non-singular lower triangular matrix. Our right-hand side, for the purpose of this example, is going to be 8 minus 4, 3. And if we write out the equation AX equal B in terms of the individual components, we're going to get 2x1 equals 8 for the first equation. The second equation is 3x1 plus 4x2 equals minus 4. The third equation is x1 minus x2 plus 6x3 equals 3. So these are the 3 equations. And the strategy is simple. You just start solving at the top, substitute in as you go down. So the first one, x1 is 4 because 2 times 4 equals 8. So we got x1. And the second one, we have 3x1 plus 4x2 equals minus 4. If we rearrange and write in terms of x2, we get minus 4 minus 3 times 4, because we just found x1 is 4, and then divide the whole thing by 4. So minus 4 minus 3 times 4 divided by 4. This is minus 4 minus 12 is minus 16. Divided by 4 is minus 4. And the third one, we've got to do 2 substitutions. We'll get x3 equals 3. x1 is 4, so that becomes minus 4 when you move it over. x2 is minus 4, so this becomes plus 4, and it's a minus 4 when you move it over. And then we divide the whole thing by 6. So here we get 3 minus 4 is minus 1, minus another 4 is minus 5, divided by 6 is minus 5 over 6. Then we got to check. So here's the solution we just found, 4 minus 4 minus 5 over 6. And we're doing A times the solution x equals b, and we're checking that everything works. So 2 times 4 is 8. That's good. 3 times 4 is 12 minus 4 times 4, which is minus 16. So 12 minus 16 is minus 4. Here we have 1 times 4 is 4 plus 1 times 4, because your minuses cancel, is 8 minus 6 times 5 over 6 is minus 5. So you get 8 minus 5 is 3. And this thing, 8 minus 4, 3, matches the original input B. So that works. So that's basically it. Those are the systems, or the kinds of systems that we know how to solve. We know how to do it when We have a diagonal. By the way, a diagonal is just a special case of a lower triangular, or an upper triangular. So a diagonal matrix is both lower triangular and upper triangular. So really you don't need this as a separate case, but we're listing it here. So we have diagonals, we have orthonormals. We know how to solve when you have an orthonormal. We looked at an example where you have kind of a combination of diagonal and orthonormal using both of those properties. So you can mix them up, so that's good. And then we have triangular systems, both lower triangular, which we worked an example, and upper triangular, which we didn't, but you can imagine that's easy as well. So basically it's just those few categories where we know an algorithm for solving the system. So that's great. But of course, not all matrices A are so nice, meaning that not all of them fall into one of these nice categories. So what the heck do you do when the matrix does not fall into one of those categories? Well, the general strategy is to find a decomposition of the matrix into nice matrices and then use solution methods for the nice matrices. So by decomposition, what I mean is to write the matrix A as a product of nice matrices and then do the solves for the product. So if that's a little bit too abstract, let's look at an example. And we're going to come back to our orthogonal example. So this was the matrix A, 1, 2, 1, 1, 0, minus 1, minus 1, 1, minus 1 in column major order. We can write the matrix A as the product of these two matrices. Just double checking. Let's see. 1 over square root 6 times square root of 6 is 1. 2 over square root of 6 times square root of 6 is 2. 1 over square root of 6 times square root of 6 is 1. So this should work out nice. So this is correct. We're not going to go through every entry, but you can double check that. So we're writing the matrix A as the product of this matrix and this matrix. And the notation I'm giving to those two matrices are Q and D. And you'll notice that these two matrices are special in that Q actually now is an orthonormal matrix. And D, of course, is a diagonal matrix. So this is an example of a matrix decomposition that's going to make our life easier. By the way, this is, this is an example of a QR decomposition. That's why I'm using the Q. And this is, technically, it's an upper triangular matrix, which is what the QR decomposition does. We're not going to cover that in this video, but we will in the next one. So this is just an example of what I mean by decomposing our original matrix into a product of nice matrices. This is orthonormal, so we know what to do with it. This is diagonal, so we know what to do with it. And when we go to solve the solution, AX equals B, what we do is just multiply, on the left. Here I'm just rewriting A as Q times D times X equals B. This is just rewriting this. If we multiply on the left by Q transpose on both sides, we get Q transpose Q dx equals Q transpose B. And then this becomes dx equals Q transpose B. So here on the right-hand side, these are known quantities, Q transpose B. This is an orthogonal transform. And the left side, we have dx. And this x is still unknown, but d is known. So this is like our new A. This is like our new B. And we know how to solve diagonal systems. So we can just get x equals d inverse Q transpose B. Okay, so this is just an example of how you can use matrix decompositions to make your life easier. All right, so the most important matrix decomposition for solving linear systems is called the LU decomposition. As you can guess, this means we're going to take our matrix A and decompose it into the product of two matrices L and U, such that L is lower triangular and U is upper triangular. So the problem becomes, the decomposition problem is find L lower triangular and U upper triangular so that A equals L times U. And then if we look at our equation, it becomes this. AX equals B corresponds to LUX equals B. And we'll show an algorithm, I'm not showing it here, that allows you to easily find X by doing a forward substitution and then a backward substitution. Equivalently, it's just X equals U inverse L inverse B. Okay, so, oh, right, here it is. So solve using the following algorithm. You solve for Y in Ly equals B using forward substitution. So this we can do. So just after we get the decomposition, we have B, we have L, and I'm setting up a system with an unknown Y. So we're solving for Y here. This is something we know how to do because we know how to do forward substitution. And we now, after we've done the LU, we know L, and of course we know B. So if you stare at this and compare it to this, Y is taking the place for UX. So it's Ly equals B. So this implies that Y equals UX. X is the thing that we want to find. So once we've found Y, now we're in a situation where we know U because we did the LU decomposition. X is what we're trying to solve for. And we know Y. And this is an upper triangular system, so we can solve it using backward substitution. That's what I mean by saying you first do a forward substitution and then a backward substitution, and that gives you X. In matrix inverse form, we have X equals U inverse Y. Just rearranging this. Y equals L inverse B, which means that X is U inverse L inverse B, and the A inverse, if A is LU, A inverse is U inverse L inverse. So this becomes X equals A inverse B. So this isn't how you do the problem. That's just showing you that this algorithm produces the solution that you want. So I mentioned this as one of the most important ones because this is the default solving algorithm in R. So let me pull up a terminal and I'll show you that. And I'll make this bigger. So I just fired up an R session and I'm going to look at the documentation for solve. All right, so solve is a function that allows you to solve a system of equations. This generic function solves the equation AX equals B for X, where B can be either a vector or a matrix. We're looking at situations where B is a vector, but if B is a matrix, that just means you're doing, so if B is a n by 3 matrix, for example, then you're getting the solution to AX equals the first column, and then separately you'll get the solution to AX equals the second column, and separately the solution to AX equals the third column. That's exactly what you're doing in generalized least squares. So in this case, we're doing multiple solutions here because X is a matrix. Okay, so what's going on here? A is a square numeric or complex matrix containing coefficients of the linear system. That's what we're calling capital A. B is the right-hand side. That's what we're calling B. Tol is the tolerance for detecting linear dependencies in the columns of A. So this is important. We talked about floating point numbers last time. And sometimes it'll happen that even if A is mathematically, theoretically, a non-singular matrix, when you start to do the LU decomposition, you run into a situation where it becomes numerically singular, meaning that you get a floating point number that's equal to 0, even though the real actual number is not 0. Skip this. This is defunct. And the details. So let me just see here. Source. Okay. The default method is an interface to LayPack, which is a bunch of Fortran routines for doing linear algebra. It's the linear algebra package. Interface to LayPack routines DGESV and ZGESV. So let's take a look at the web page for DGESV. I've got it pulled up here already. DGESV, this is a LayPack function. And let's see, purpose. DGESV computes a solution to a real system of linear equations, AX equals B. And then it says here the LU decomposition with partial pivoting and row interchanges is used to factor A. So factor means decompose, as A equals PLU, where P is a permutation matrix. Well, we haven't introduced P yet, but we will. L is lower triangular and U is upper triangular. So by default, when you call the solve function in R, it is calling this LayPack routine, DGESV, which uses an LU decomposition. So that's what I mean when I say the default method in R for solving is to first compute an LU decomposition. By the way, the other one here, there's DGESV, which we just looked at. And there's also ZGESV, which is just the same algorithm, but for complex matrices. All right, so let's get out of here and let's get back to the notes. Yes, this is the default solving algorithm in R. All right, next question, you're probably wondering, how do you do the decomposition? Or in other words, how do you find the L lower triangular and U upper triangular such that A equals L times U? So I write here that the strategy is not too complicated, but I guess you can be the judge of that. And here's how it works. Find a sequence of n-1 lower triangular matrices, call them M superscript 1 up to M superscript n-1, such that the product, so I guess you can read it this way, M1 times A multiplied by M2 times M1 times A, all the way up to mn-1, mn-2, down to m1 times A. This is going to be a matrix. And we find a sequence such that this matrix is upper triangular. So now we have something times A equals upper. That's the first step. And if we know that the product of lower triangular matrices is lower triangular, and also the inverse of lower triangular matrices are lower triangular. I'm not proving that to you, but we'll just take that as true. We define L inverse to be this product, mn-1, all multiplied down to m1, which is this set of matrices. Then we have L inverse A equals U. And if we just multiply on the left by L, we get A equals LU. Okay, so that's the general strategy. We have to tell you how this gets implemented, but we have to find the sequence of lower triangular matrices, which produces an upper triangular on the right when multiplied by A, and then we just flip the product of the sequence of matrices around to the other side, and that gives us A equals LU. All right, so how do you do this? This is through a process called Gaussian elimination. You probably learned this in your matrix algebra course, but we're going to review it here. So here's how the sequence works. The first matrix, M1, has the following form. It's a diagonal matrix plus some extra stuff here in the first column. And the extra stuff is minus A21, A11. Remember, this is the 1, 1 entry of A, the original matrix. This is the negative of the 2, 1 entry of A. And you can see how the pattern works. In the 3, 1 entry of M, you get minus A31 divided by A11, all the way down to the N1 entry of M1. You get minus AN1 over A11. Okay, so why did we do this? If you multiply this by A and call that A1, something interesting happens. So if we do, let's just do, let's do the 1, 1 entry. So it's going to be this row multiplied by the first column of A. So it's going to be 1 times A11. So we get a non-zero entry here. However, if we go to this one, we're going to get this times A11, which is minus A21, plus 1 times A21. And those cancel out, and you get a 0. Do the next one. This is going to be, multiply this by A11, you get minus A31. And then there's going to be a 1 here, which gets multiplied by A31, and it cancels with that. So you get another 0. And if you continue this, you see you get all zeros down here. So it may be helpful if you just write out the matrix A next to here and just go through the multiplications. Now, I'm not telling you what these numbers are, the non-zero ones, in terms of A, but they're just functions of A and this M matrix. And I'm giving them the notation superscript 1. So it's just enough to know that you get zeros in these positions and something else in the other positions, and we're giving that a notation. Now, the second matrix, M2, is constructed in a very similar way, except now we're putting, so we have a diagonal identity matrix plus some extra stuff. The extra stuff now goes below the diagonal in the second column, and we're using the entries of this matrix, which is M1 times A, to define the entries of M2. And you can see the pattern's very similar. So I won't go through the details of the multiplication, but you can do that yourself. What this ends up doing when you multiply it by A1 is you eliminate, so you leave these zeros untouched, they remain zeros, but it eliminates the zeros below the diagonal in the second column. So I'll leave that to you. It's the same sort of thing. If you multiply this, if you multiply this, well, let's do the first one just for fun. So we're looking at this entry. So this is the 3, 2 entry. So it's third column multiplied by the second column here. So you get minus A32 it's 0 times A12 is 0. Minus A32 divided by A22 multiplied by A22 gives you minus A32 plus 1 times A32. So you get minus A32 plus A32 is 0. And then you can see the pattern is going to be the same for the other ones as well. So that's why you get all zeros here. This is called Gaussian elimination. Basically what happens is with each successive matrix multiplication, you set this to 0, and then you get new entries here. So this is defined to be A2. So this continues until you get mn minus 1 times an minus 2 equals an minus 1, which has eliminated all of the entries here, and which leaves you with an upper triangular matrix. So the notation I'm using for the n minus 1a is just U, an upper triangular matrix. So this is how Gaussian elimination works. If you're not convinced, go ahead and take out a sheet of paper and write out the matrix multiplications. So what have we done so far? We have established the first part. We found a sequence of n-1 lower triangular matrices such that if you multiply them together and then by A, you get an upper triangular. So this is true because we define A1 as M1 times A, and then we multiplied A2 by A1. So, and then we built everything up. The next step is to figure out what the inverse of the product of these matrices are. So the product defines L inverse, and we have to get the inverse of L inverse, which is L, and use that on the right-hand side. Okay, so that's the next step. Okay, the inverse of this product is just the product of the inverses in reverse order. So we have to look at what are the inverse of these individual matrices. So it turns out you can write the kth matrix M in the following way. I minus lowercase m times the identity vector ek. So what do these mean? So, sorry, this is called the unit vector k. So this, we'll define it this way. So m sub I, mk is a vector. Its ith entry is the following. It's 0 if I is less than or equal to k. So that means the first few entries up through the k minus 1 entry, or actually up through the kth entry, are all 0. And then down below, you get this ratio, aik minus, or divided by akk. So these are the entries of the big matrix, capital A, superscript k minus 1. If you're wondering where the heck does this come from, this is simply this vector without the diagonal entry. So it's going to be 0, 0, and then this stuff for M2, lowercase m2. So that's all it is. And then M is equal to I minus mk times ek transpose. So ek is the kth unit vector. All this means is that the kth entry is 1 and is 0 otherwise. So you've probably seen this. This is kind of sometimes called the unit basis in linear algebra. So if we do mk times ek transpose, what we're going to get is a matrix that's all zeros except for these entries down here. And you can see that if you do the identity matrix minus that matrix, you get exactly this matrix. Okay. So maybe that's overcomplicated things, but to write it in this form. But you'll see it actually makes our life easier to define the inverse. So I'm going to claim that the inverse of this matrix is I plus that outer product. And all we have to do is do the math and show that it's equal to the identity. So it's going to be I minus this times I, which is this, plus I times this, which is this. And then the last term is going to be minus mk ek transpose times mk times ek transpose. And you'll see the inner part is an inner product. So it's ek transpose times mk, which is the dot product of these two vectors. And since this is the unit basis, what it does is the dot product just pulls out the kth entry of this matrix, or this vector, which is 0. So the dot product here is 0, which means that this whole term is 0. And this cancels with this. Therefore, you get the identity matrix. So that proves that this is the inverse of this. Okay. So that's nice. We actually know exactly what the inverse of this is in terms of these, the identity matrix and the outer product, these two vectors. So it's this thing here. Okay, that makes our life simple. This Gauss guy was pretty smart. The other thing is that if you look at the product of successive ones here, so this is M1 inverse times M2 inverse. Why are we looking at this? Because we have to, in order to construct L, we have to take the product. Something interesting happens here. So it's this. If we multiply this out, we get something similar. I plus M1 E1 transpose plus M2 E2 transpose plus this inner term. So M1 times E1 transpose times M2 times E2 transpose. And if we look at this inner part of this product of these four vectors, you get this thing is just pulling out the first entry of M2. And the first entry of M2 has to be 0 according to this definition. Therefore, this inner product is also 0, and this goes away. So that makes it kind of nice because I know that the product of these two matrices is just I plus M1 E1 transpose plus M2 E2 transpose, which we've already calculated in finding the M's. So that's nice. And then I won't go through this, but if you continue doing this, you know, multiply the third one there, you'll see that the same pattern emerges because these inner products evaluate to 0 and eliminate some of the terms. So this really should have 6 terms, but it only has 4 because some of them are 0. And then if you continue this pattern, you'll see that L is just equal to I plus these outer products. So what that means is we don't actually have to calculate the inverse. We just know what it is. And we don't actually have to do the matrix multiplications to calculate this product. We just know what they are in terms of the M's and the E's. So that's really convenient. So if you put all this together, now I know what U is because I did this multiplication. And I know what the M's are from that doing that Gaussian elimination. And by storing information along the way, namely these entries, storing those along the way, I automatically know what L is. So therefore I have L and U, which was the goal of this algorithm. Okay, you may have peeked down below, and you'll notice that there is a catch. So let's go back. Well, let me tell you what the catch is. This AKK superscript K minus 1 could turn out to be 0. And in the book, there's actually a very simple example where it does turn out to be 0. So if that happens, you run into a problem. So let's look at this. Okay, actually, let's just look at this first one. So if the matrix A had a 0 in the 1, 1 entry, then we are totally out of luck because we can't even form the first matrix M1 because we would try to do minus A21 divided by 0 and we would be stuck because can't divide by 0. So, and this could happen anywhere along the way. So suppose the first one works, but we get to the second one, we do this multiplication, and we find that A22 is 0. Then when we go to form M2, we're going to get minus A321 divided by A221, which is 0, and we're out of luck. So this could fail at any step if the this diagonal entry, the KK superscript K minus 1 entry is 0. So what do you do here? So this is the default method in R, so it must work pretty well. And it must work when the 1, 1 entry is 0, because there's no theorem that says that if the matrix is singular, if the 1, 1 entry is 0. So it has to work for those kind of matrices. So what is done in practice is, you may have noticed when we looked at the documentation for DGESV, it says it does something called partial pivoting. And here's what partial pivoting does. If you run into a situation where this entry is 0, so you're doing this algorithm, Gaussian elimination, along the way, and you find an entry that's 0, you can't do the division. The solution is to just look at the lower rows. So back here. So if this ends up being 0, you look at these lower rows and you just pick the largest one and you swap that row for this row. And you'll notice what happens, you actually don't screw anything up. The pattern of, by that I mean that the pattern of the matrix is the same. You now have a non-zero here by swapping in this one. And you haven't messed up these entries. They're all still 0 because if you swap any of these, you're still going to have a 0 here. Okay. So you do this swapping. And then you just continue with the algorithm. Now these swaps are represented by what's called a permutation matrix. So a permutation matrix, if you multiply it by another matrix, basically what it does, it'll swap the rows or the columns. And the full LU decomposition that's actually used returns not L and U such that L times U equals A. It returns L and U such that L times U equals a permutation of the rows and columns of A. And that's represented by PA equals LU. If you remember back to the DGESV documentation, it was actually A equals PLU, but that's kind of equivalent because permutation matrices are orthonormal. So if you just do P transpose times P over here, you get P transpose LU here. So I'm not going to go through the full algorithm for how the pivoting works, but that's what it, that's the intuition for how it works. You just swap the rows. It's complicated to go through the whole thing just because you have to keep track of these permutations and you have to keep track of how these M vectors work. You actually don't use the original M's. You use this permuted version of the M's to construct L. But this is the formula. This is in the book. If you want to go through all the details, you can follow, I think it's exercises 3.2 to 3.6 to go through all the details of how this works. But it's kind of just like annoying bookkeeping. It doesn't really give you a whole lot of intuition. But I think showing how it works without pivoting gives you the major idea. Okay, so this is what actually happens. It's slightly different. You have these swaps. Okay, so I claim that it was pretty, what did I say? Not too complicated. Well, it is or it isn't. Only took a couple pages. All right, so let's do a simpler one. And hopefully you'll at least agree that this is simpler. The simpler one is called the Cholesky decomposition. Some people say Cholesky, some people say Cholesky. I say Cholesky. Don't hate me. All right, so this works in the special case where the input matrix A is symmetric and positive definite. Symmetric positive definite, there's various ways to define it. The simplest way is to say, if I take any vector x and I do x transpose AX, I'm going to get a positive number. You can also define it by looking at the eigenvalues of A. So if all the eigenvalues of A are positive, then A is positive definite. Okay, so the Cholesky decomposition solves the following problem. Find a lower triangular matrix L such that A equals LL transpose. So if we look back at, so why is this important? If we look back at our generalized least squares, you have B hat equals X transpose sigma inverse X inverse times X transpose sigma inverse Y. Now there are three inverse matrices here. There's sigma inverse again, and then this product inverse, X transpose sigma inverse X, all inverse. All three of these, well, there's actually only two because the sigma is repeated. So both of these are symmetric positive definite matrices. Sigma is a covariance matrix, which must be, by definition, symmetric and positive definite. And sigma inverse is also, the inverse of a positive definite matrix is also positive definite. And anytime you do something like this, X transpose times positive definite times X, you return a positive definite matrix. Technically, it could be non-negative definite, which means that one of the eigenvalues is exactly 0. But let's just say it's positive definite. So the Cholesky decomposition is useful because it allows you to do easily the calculations for generalized least squares. So this is a special case, but it's a very important special case for statistics. So you could just use Gaussian elimination, the LU algorithm, and that would give you L and U, and they should be equal. L should be equal to, or so U should be the transpose of L. However, there is a simpler and faster algorithm for getting L when A is symmetric and positive definite. And here's how it works. First, some notation. I'm going to define A superscript K. So this is a different definition. I'm using the same notation as in Gaussian elimination, but now has a different meaning here for the Cholesky decomposition. This just means the upper left K by K submatrix of A. So if I were to write out the matrix A in block form, it would look like this. So the upper left corner, K by K corner, would be A super K. And then there would be extra stuff. So I'm just representing extra stuff with these stars. Now the matrix we're trying to find is L. And let's define L superscript K to be the upper left K by K submatrix of L. So if this matrix is L, all this means is that LK goes here. There's stuff down here, extra entries. But we know since this is lower triangular, you're going to have zeros up here. All right, so if we write down the whole thing, we get A equals LL transpose. And if you do this multiplication, so AK is going to be L times LK times LK transpose plus 0 times 0, which means that AK equals LK transpose. Now this is the Cholesky decomposition of AK because LK is lower triangular and we're multiplying it by its transpose to get AK. What this means is that if you can find the Cholesky decomposition for this upper K by K submatrix of A, and you can use it in figuring out the Cholesky decomposition of the next one, A super K plus 1, then you can come up with what's called an inductive algorithm, which just means you go build it up step by step to find the Cholesky decomposition of the whole thing. So here's how the inductive algorithm works. So when you do like a proof by induction in math, basically you have to show that you can, that whatever you're doing works for the first step in the induction. And then what you have to show that the induction works is that given the solution at the kth step, there's a viable or correct method for getting the solution at the K plus 1 step. So that's what we're going to do. We're going to show it works for the first step. We're going to assume it works for the kth step and show that you can use that to get the K plus 1 step. So the first step, A1, is the upper left 1 by 1 submatrix of A, which is simply the entry A11. This is going to be equal to L1 transpose. And this is just the L1 is just the 1, 1 entry of L multiplied by itself, because the 1, 1 entry of the transpose is still the 1, 1 entry. So this is L1, 1 squared. And therefore, L1, 1 equals the square root of A1, 1. Okay, so that's simple. That's the first step. Given this matrix, we know how to get the 1, 1 entry of this Cholesky decomposition. The next step in induction is to assume you have the solution for the kth step and show that you can find the solution for the k plus 1 step. Okay, so here's the solution for the k plus 1 step. You can write it out in the following way. The upper k by k submatrix of the k plus 1 step is just the upper k by k submatrix of A. And then you have extra stuff, but now I'm going to write out explicitly what the extra stuff is. My notation here is that this extra column, so this is going to be a, let's see, k by 1 vector. We're calling that lowercase a superscript k plus 1. That goes here. Transpose of that goes here. And then this is simply the k plus 1 entry of A. So this is the upper k plus 1 by k plus 1 submatrix of A. We're just writing it out in slightly different notation. By the way, this is always just given to us. We know what all of these are. And the task is to figure out the stuff over here. So let's write out the LK plus 1. Well, the upper left is going to be LK. And then we have extra stuff down here. This is going to be a 0 because it's a 0 vector, k by 1 vector of zeros, because it's a lower triangular matrix. The first k entries of row k plus 1, we're writing as LK transpose, lowercase. And this is just the k plus 1 by k plus 1 entry of L. And this is simply the transpose. So this is LK plus 1 times LK plus 1 transpose. Now, what do we have to do to get LK plus 1? We have to figure out what these entries are. So basically what this next row is, which is equivalent to finding out what this column is. And basically the way we do this is we just kind of multiply these together and set up a system of equations and solve for it. So if we do LK, so I want to do this vector. And this is equal to LK times lowercase lk plus 0 times this. And I have a typo here. This should say a k plus 1. So this thing I wrote v is really this. And is equal to lk times lowercase lk. Now, the goal here is to figure out lk, this lowercase lk. This is the part that's not known at this step just yet. But you can see that, so this side is known. This is a k plus 1. This is just taken from the matrix A. And we've set it up so this is a lower triangular system. L is lower triangular multiplied by a vector equals something we know. And therefore, we can use forward substitution to solve for lowercase lk. So we just do a lower triangular solve to get lk. So that gives us, let's see, that gives us, we know this, that gives us this. And the only other thing we need to know is to figure out this entry. But we can set up another equation. So we know that a k plus 1 comma k plus 1 is going to be equal to lk transpose times lk plus lk plus 1 comma k plus 1 times itself. So that gives us this equation. And it's this. And now, since we already know L super K, we can just solve for the thing we don't know yet. And that's simply this. Okay. So that concludes the, and then you repeat. So that includes the induction. So this is the algorithm that's used to compute the Cholesky decomposition of a matrix A. Basically, you build it up step by step using the knowledge that the upper K by K submatrix of L is the Cholesky decomposition for the upper K by K submatrix of A. And then you have to do some lower triangular solves and a little bit of algebra to figure out what the next row of L is. By the way, before we conclude here, this looks like kind of a dangerous operation. So what happens here is in order for us to take this square root and get a real answer on the left side here, this number, this diagonal entry of A, has to be larger than this inner product. And due to floating point rounding errors, it's possible that even if A is symmetric and positive definite, that you could run into a situation where this evaluates to a negative number, and therefore this ends up being complex, and that screws everything up, and your code will throw an error. Another thing that could happen is that this number is very close to 0, and so that will automatically give you something that's negative here. So there could be floating point issues. It could be the case also that you didn't know it, but you gave your algorithm a matrix that's not positive definite, meaning it has a negative eigenvalue for real, in real life, in real math. And doing the Cholesky algorithm will detect that by finding that this difference ends up being a negative number at some point during your Cholesky inductive algorithm. So, and in that case, your code should throw an error, and that's what you're going to do in the exercises. Now, it's actually kind of useful because the Cholesky algorithm is used to detect whether or not a matrix is positive definite. So if the algorithm fails because you get a negative number here, that tells you that, at least numerically, in the floating point system, your matrix is not positive definite. Okay, that's it for today. So what did we cover? How to solve linear systems when you have a very simple matrix. And then we covered two methods for taking your input matrix when it's not simple and converting it to a decomposition that gives you a simple matrix. So I guess I didn't explicitly mention it, but if you can take your input matrix A and write it as LL transpose, you can use the same algorithm we used to solve for x in AX equals B by rewriting it as LL transpose X equals B, doing a forward solve and then a back solve, and then that will give you X, just like in the LU decomposition. So that's the general strategy. If you don't have a nice input matrix, you can decompose it and use the simple methods to solve systems using the decomposed matrix. So next time we're going to talk about more such decompositions.